In example 6.5.2, finding probabilities for sample means, we're going to look at an example. The most famous geyser in the world, Old Faithful in Yellowstone National Park, has an average time interval between eruptions of 85 minutes, with a standard deviation of approximately 21.25 minutes. This random variable is not normally distributed, though it is somewhat mound-shaped. So we're going to go through and look at this, this problem. Notice we find that we have an average. Remember, when you're talking about average, let me find my pen here. When we talk about average, that's the same thing of mean as a mean. So we have a average time interval between eruptions of 85 minutes. And then we have a standard deviation of approximately 21.25. So that's some important information. Notice also it states it is not normally distributed. So if it's not normally distributed, what that means is we need to have our n be greater than or equal to 30. Okay, so we're going to go through and identify the individual in this problem, the random variable x in the context of this problem, and also we're going to write out our given information with correct symbols. So notice, first of all, the individual would be an eruption of Old Faithful. Okay, so we're going to be looking at one individual. And then our random variable x is actually, we're examining the time interval between eruptions. So our random variable x is our time interval between a randomly selected eruption of Old Faithful. So the Old Faithful will go off, and then it'll come back down, and then we start counting times between it. So when it goes back up, and so we have an eruption between, we're looking at the time between. Now, notice it gave us the mean of our variable x, which is 85 minutes. On average, this thing erupts every 85 minutes. So that's, more than an hour between times. Our standard deviation is 21.25 minutes. Also, it told us that the distribution is not normally distributed, but that means we need to have a sample greater than 30 so we can assume normality. So let's look at part B. Part B, suppose we have a sample of 35 time intervals is taken. Find the probability that the mean time of the intervals of those 35 eruptions is longer than 95 minutes. So that's a good thing. Notice here our n is greater than or equal to 30, so we can assume normality because our sample size is large enough. Notice they're asking us to find the probability that the mean time of those 35 samples that we're looking at is greater than 95. So we'll write P, and then P is the probability of X bar, because we're now looking at the sample mean, and it's greater than 95. So our random variable of the means in this, of the sample mean, if I'm going to interpret this, it's the mean eruption time of the 35 randomly selected sample of eruptions. So random sample of eruptions, 35 of those. We find the average time. So that's what our X bar represents, our mean. Now, all the information that we see in this problem allows us to continue on by using the central limit theorem. So even though the original random variable is not normally distributed, the sample size is 35, which is greater than or equal to 30. So by that, we can use the central limit theorem. So by the central limit theorem, the sampling distribution of the mean will be approximately normally distributed. Okay, our central limit theorem told us that as long as we had a large sample, or it said our sample was from a normal population, we could use it. The only thing that changes in the central limit theorem will be our standard deviation. That's the only part that changes. So now the mean of our sample means is going to be the same thing as our population mean. If you look back at the original problem, the population mean was 85. Our standard deviation was 21.25. So we have to make an adjustment for the central limit theorem because we're looking at sample means. And our formula says the standard deviation of the sample means, it's the standard deviation of x divided by the square root of n. Well, our standard deviation of our x value was 21.25 divided by the square root of 35. We will use this in our calculator to find our probability that our sample means is greater than 95. Okay, so you have all the information you need to use the normal cumulative distribution function. And if the sample size had been less than 30, the central limit theorem could not apply. So you couldn't use the normal distribution and you would not be able to answer this question. But in this case, we can. And we're going to use Desmos to do this. So I want to open up Desmos and show you where we're going to go. So let's type in desmos.com. If I can spell. Desmos.com, and this comes up. Now, what happens is a lot of times I forget the commands I need to use. So I'm talking about a normal distribution. So I'm going to come down to the small keyboard that says Show Keypad on Desmos. So I'm going to click that. And then this calculator will come up. We're going to click Functions. We're going to come down. Now here's Statistics, where we've used operations before. But we need to come down to a distribution. We're going to do a normal distribution. So notice it pulls up for us. It tells us to put in the mean and put in the standard deviation. So our mean was 85. We got to put a comma. And then let's go back and look. We need to put in this 21.25 divided by square root of 35. So 21.25 divided by, now the square root is down in our calculator, square root of 35. Now, I made a mistake because I accidentally put, and notice, you'll know this because it'll put exclamation. It says, sorry, I don't know what to do. I put a period instead of a comma. So I'm going to fix it. And so now it should work. I'm still messed up. What did I do? Oh, I see what I did. Let's fix it again. And it makes you make mistakes, just fix them. So we have that. We have normal distribution, parenthesis 85, comma, and now I'm going to kind of hit a space. And I'm going to type in 20, I forgot what my number was, 21.25. And this is, if you make a mistake, just go back and try to figure out what you've done. 21.25 and then divide. So before it was dividing the 85 also. So I don't know how it did that, but anyway, then I hit my square root and then 35. There we go. And now it's starting to work. So notice how if it doesn't work, it'll give you an exclamation point. So normal distribution, we have 85, comma, and then 21.25 divided by the square root of 35. And I'm going to click the magnifying glass to make this fit. So there's my equation. Now I need the probability that my sample means were greater than 95, I believe. Yes, I need greater than 95. So when you come down, click Find Cumulative, and we need 95 as our minimum. Because we need greater than 95, you can see the shading that it's greater than 95. And there is our probability, 0.003. okay? So if you make a mistake, just go back, start all over and try to find out. Notice mine was, I accidentally somehow made a fraction out of the whole thing. So I just started all over. So here we go. There is our probability, very unusual. Remember, if you have the probability is less than or equal to 0.05, that's unusual. So ours is. So the probability of a sample mean of 35 eruptions is very small. It's 0.003. This is extremely unlikely to happen. It's unusual for it to happen because on average, there's 85 minutes between eruptions. We were looking at 95 or even higher minutes. If it does, it may make you wonder about the sample. Could the population mean have increased from 85 minutes? Maybe the population mean has changed. Or could the sample not have been random and instead the sample was collected maybe using a convenient sample? Maybe you had a bad sample. These questions and more are ones that you would want to ask as a researcher.